Maybe.
It's very
Not really.
difficult for us to stress on some. So
I see. I really want to use it sometimes.
TC would be a lot.
I think it's a really cool. Yeah. What else? Yeah. Everyone's dying. It's so fun. Like watching people at the summit at the end. Like, have that friend do it. Yeah, they all just look so
Anyone ever did. All right, welcome everybody to the departmental colloquium. Very pleased today to be introducing Salil Mahajan, who will be giving our talk today. So, I actually first became aware of Salil's work when he was a graduate student at Texas A&M, working with Sarah Vaughan, but also you had done some stuff with Ping Chang as well.
yeah, he was my coach.
Yeah. Where he was looking at RFC feedbacks in the tropics and doing things like turning on and off different physical processes in CESM, and doing some very creative work with looking at the response of the climate system to some of those changes. And then he ended up helping out one of my students in doing a similar set of experiments in CESM around that time. Salil went on to Princeton to do a postdoc with Rong Zhang and Tom Delworth, looking at AMOC and AMOC fingerprinting, and then moved on to Oak Ridge National Laboratories, where he currently is a senior scientist and the group lead for computational hydrology and atmospheric sciences. Salil's work spans a lot of different areas, which has been a lot of fun to kind of follow and to see. Everything from application of different statistical techniques in creative ways to forecasting and climate problems, to looking at aerosol variability, hurricane activity.
Yeah, not yet, not too much. But
Okay, I was thinking of and application of machine learning, both in the standalone and in looking at machine learning emulators for model parametrizations as well. So a lot of interests that overlap with interests that we have here as well. So a few years ago, when we applied for a project at DOE, and we're looking for collaborators, and it was a no-brainer for me to call up Salil and see if he would be interested in collaborating with us on a project looking at seasonality of sulfate aerosols, and he's been collaborating in that respect with the project that we have here. So, very glad to finally get you up here to Wisconsin, and looking forward to your talk today.
sure, thank you. Hi everybody. So my topic of the day is ENSO teleconnections, and so I've used it in a couple of ways, or I'm talking about it in a couple of ways. One is how do Earth system models simulated in different situations or different configurations. So by I say a resolved scales hierarchy, by that I mean low-res simulations, high-resolution simulations, and a configuration called the multi-scale modeling framework, where you embed a cloud resolving model in each grid box. I'll talk more about that. And then how do we use the signals that come out of the tropical Pacific for predictability? And we know that seasonal forecasting models don't do a very good job at certain places, and assuming that machine learning can do some magic, we want to see if we can use it to extract some predictability from the tropical Pacific. So kind of a physics-informed machine learning, but in an informal way. And I'm from Oak Ridge, and so I'm part of the computational hydrology and atmospheric sciences group. I wanted to add some slides about what the group does, but I forgot to do it until like last minute. So let me just talk a couple of projects that we're involved in. So it's about 8 people, I think, and we have people who are spanning in aerosol microphysics, cloud microphysics, but the keyword here is computational. So we also have people who work on accelerating codes like MPAS Ocean, even MPAS Atmosphere these days, accelerating the UK Met Office's unified model on hybrid architectures. And we have people who do like dispersion modeling in our group, and there are also people who do hardcore machine learning for stream flow predictions and for subsurface modeling. and we have a person who just won an early career award from the DOE, doing some machine learning for E3SM. And let's see. Yeah, that's about it, but I can talk more if somebody's interested in the group. Right? And this is a collaborative work with lots of people across the DOE complex mostly. And so let's get started. So the motivation, so the last 10 years, at least in the DOE world, has been spent on increasing resolution of the Earth system model that we have. We started with CCAM, and then we moved on to DOE's own model, the E3SM, which stands for the Energy Exascale Earth System Model. And the reasoning behind was that we have a big machine which we can now use to do high resolution simulations, and we wanted to see what benefits come with doing a high resolution simulation. And studies have shown that with high resolution you can resolve more fine scale features, you get realistic orographic lifting, coastlines, simulations around them, so scale eddies in the ocean, we can improve variability, mean, certain things like tropical cyclones, extratropical cyclones too. And then another big thing is they also simulate stronger extremes, just because you're resolving more fine scale features, so you can get stronger uplifts in the model, and which might result in stronger precipitation, for example. And then we want to look, since we have this and then so resolution is not just the domain for the global models. It has been done in regional models for a long time. But then if you look at global scale processing feedbacks of these highly resolved processes on the local scale to the global scale, that is being missed in the regional models. So now in this case, you can have a real case where you can study ENSO teleconnections, which has this global forcing on a local process, and maybe there's some impacts on the outside regions of your region of interest. So it's more like studying an embedded process in the high resolution where the whole globe is resolved. And so we wanted to evaluate the teleconnections ENSO to extremes, and we focus on winter precipitation, where convective precipitation is subdued, so we don't have to worry about parametrizations of convection largely. And then we use the generalized extreme value theory to capture to quantify extremes. And then we looked at some plausible drivers of why this happens. And then we also look at some diversity of ENSO, which is a hot topic these days. And further, now we have this multi-scale modeling framework, as I talked about a few minutes earlier, where you resolve deep convection. So that means we can get rid of some of the errors from deep convective parametrizations, theoretically. And we know that if you look at the ENSO teleconnections that are caused by emanation of Rossby waves from the tropics, and so once you resolve deep convection properly or more accurately using this MMF framework, maybe you will have a better teleconnection. And so that was our hypothesis that we wanted to test with this model too. And let's see, I have to say, so the way it's done is it's also called superparametrization, where you take each grid box and you add a 2D cloud resolving model in there, which makes it expensive, but it's still feasible on a big machine, and you can do that and it resolves deep convection explicitly, so you take away the deep convection parameterization completely in the model. And so the null hypothesis, as I mentioned, is that E3SM MMF will probably simulate the ENSO teleconnections accurately, and again we look at the winter season. Just a brief quick background on ENSO. So this, what you see is the mean surface temperature, the blue line is the cold tongue, and this is the 2024 anomaly that we saw this year, strong ENSO event that had a credible impact on, a strong impact on California, for example. And then what happens is there's a zonal wind stress that gets weakened in the tropical Pacific that causes the convection to move from here to eastwards, which emanates these Rossby waves that result in teleconnections in the other regions. And you have a plot there, just a cartoon, showing that it can increase precipitation over the southern U.S., dry the northern parts, and then also bring in colder in the southern U.S. But then it's not as simple as it looks. It could get complicated because of the ENSO diversity. Each ENSO event is very different from the other, and I'm showing two plots here from a recent paper. And this is the canonical Nino, which is the 97-98 is a very strong canonical event, for example, with strong warming in the eastern Pacific. But 2015-2016 was also a strong El Nino event if Nino 3.4 is your index. And in that case, we got a strong warming here, but not in the Eastern Pacific. And that had very different responses in precipitation, which is shown in color over the US, for example. So in 1987, it caused a large amount of precipitation over California and Southeast US, but during 2015, 2016, the prediction based on something like this was that it would produce strong rainfalls here, but it didn't, and there was almost a negative anomaly in the California region. So the question now is, can our models do all this given their large sources of errors? So we look at a bunch of models, and not just E3SM, we also look at the high-res MIP catalog, which consists of at least 6-7 models, each with at least one ensemble and one ensemble member. These are costly. Even with E3SM, we only ran one ensemble, and this is mostly looking at control simulations, which means that it's 1950 prescribed forcings for greenhouse gases and aerosol forcing. And we have E3SM1 we looked at, which has a low resolution model and a counterpart high resolution model. E3SM-V2 is slightly different. We have a low resolution model, but the high resolution model is not global. It is just a North American regionally refined model. So the resolution is only increased in that region to 25 kilometers. And in E3SM-V1, the high resolution model was 25 kilometers globally. And then the other models with different resolutions for the atmosphere and the ocean. And in most of the cases, both the atmosphere and the ocean model resolution were increased. And yeah, so we have different models. The other thing was this E3SM and E3SM2 use the similar ocean model, and these other models in the high-res MIP catalog all use the same ocean model, which is NEMO, more or less. Maybe Hadjim has a different model, but more or less all of them use the same ocean model. And so this is and we also look at E3SM MMF, which is, as I mentioned, a DOE's modeling configuration. It's a 2D cloud resolving model in each grid box with 64 columns. The global resolution is 100 kilometers, and within each of those 100 kilometer grid boxes, we have these 2D resolving cloud resolving models. The physics are simpler than E3SM. V2, it's a single moment cloud microphysics, and it has prescribed aerosols as opposed to diagnostic aerosols, prognostic aerosols. And then it was run on Oak Ridge's Frontier machine, and it has been accelerated for hybrid architectures like that, trying to use a big portion of that machine. And now we have one historical fully coupled run, so it goes from 1950 to 2014, and it's coupled to the impasse ocean too, just like the other E3SM models. And so we validate these model simulations with gauge-based precipitation data, as well as GPCP, as well as gauge analysis to study the drivers of the extremes that we find. So the methodology for computing extremes, we use the generalized extreme value distribution, which is a 3-parameter distribution, mu being the location parameter, sigma being the spread of the parameter, and g being the thickness of the tail parameter. And theoretically, what this means is that if you think about a mean of a process, then it's probably estimated by a Gaussian process, which is the central limit theorem. Similarly, the extreme of a process can be said to belong to the GEV distribution of families, and it's analogous to the central limit theorem just for extremes. And then once we have, if you model your extremes using a PDF, that means you can also model it as a generalized linear model, which means you can have the PDF as a transient, which means that you can have something like, if you take the location parameter, you can add another parameter to it, which depends on something else. So in this case, it could be a time trend, for example. So you can assume, you can foresee a situation where you know that the PDF is changing in time, say with global warming, and you can add that term in there. So now instead of 3, it becomes a 4-parameter distribution, where t is time and alpha is your new parameter. And then you can estimate how the PDF is changing with time. And in this case, we did this with the Nino index, with any Nino index, so Nino 3.4 index or some other index. You can put that in there, to understand the effect of ENSO on extremes, for example. And the way you estimate these parameters is through maximum likelihood, which means that all you try to do is you take the observations and you try to fit a PDF which maximizes the likelihood of those observations. So it makes these observations central to that PDF. So it tries to make sure that all the observations that you are near the center of the PDF, and then you can estimate the rest of the distribution. And then one benefit of this is that if you have a distribution like that, then you can invert it, and that gives you return periods. So like a 20-year return period for a flood event, for example. So let's look at some of these results. So this is a different paper, which is very recent, not my work, but they looked at these high-res MIP simulations, all of these, and they have the same ocean model. And what they did was they looked at the ENSO simulation in that model. And what we see here is that, so this is the observations. So this is looking at the composite of ENSO events or El Nino events in the observations, in the high-res model, in the low-res model. And this horizontal line, or this vertical line here, is the zero line for this color plot, right? So meaning how far does the warming extend during an ENSO event on an average. And we see that in the low resolution model, there's this big expansion, big westward expansion of an El Nino, but this is reduced in the high-res model. And what they found was if you increase the ocean resolution, you reduce this bias, but if you increase the atmospheric resolution, you do not reduce that bias too much. And that's true for both El Nino case and the La Nina case. And so and what that means is once you have this reduction in the westward expansion bias in the models, it means you're also having an impact on convection. And so this plot is for observations, that's for high resolution, and that's for low resolution. And you see that in the low resolution, the precipitation extends much westwards, and the reduction here is not as strong as what you see in the observations. So this means that the Rossby waves that emanate from this increase in precipitation have interference from other places, and they have a different response as opposed to what you see in observations. And in high resolution model would have a better simulation likely of teleconnections. And again, from the same paper, what they're showing is that with increase in resolution, although the teleconnection patterns in high-res models are slightly better than the low-resolution models, but they're better only in terms of the spatial pattern and not in terms of magnitude. And this is likely because of the deep convection parameterization of the model. And this is looking at E3SM only runs here. This is E3SM V1 case, and similar pattern, just looking at EUFs instead of a composite. And what you see this on the top is the observations. The middle is the low resolution, and you can see that there's a westward expansion in the model. And once you increase the resolution in E3SM, we don't see that increase. And so this means that what we see, the resolution is not really an elixir which will solve all your problems, and because different models give a different response. In the previous case, we had a NEMO ocean model. In this case, we have the MPAS ocean model, but the atmospheric resolution in those models didn't help, and it didn't help in this case too. And this is the E3SM MMF, which is the cloud resolving model embedded in each grid box, and we see the same thing. It's different color bars, but you can see that there's a westward expansion of the SST anomalies in the MMF2, which means that the precipitation response again is very different, and the weakening of precipitation here in the model is much weaker again, and precipitation extends westwards, and it's slightly weaker than what you see in the observations, which means that teleconnection patterns would be different and the response would be different. And now we can compare this ETSM MMF with the V2 model, which is very close to what the ETSM MMF has, except for the deep convection. And you can see that it doesn't really change the westward extension, but it does reduce the biases that occur in the low-res model or in ETSM V2. So this side is the ETSM V2, that is MMF, and these biases are much weaker than what you see in the E3SM V2 round, meaning that in resolving deep convection explicitly helps with reducing the biases. And so in ENSO, there are these two feedback mechanisms. One is the positive feedback, the other is the negative feedback. The positive feedback is the negative feedback is the short wave heat flux, which means if you increase, it could be positive or negative. The negative ones are if you increase your SSTs, then you increase deep convection in deep convective regions, which would increase the amount of clouds and which would reduce the amount of radiation that reaches the surface, which means it reduces the SSTs, so it's a negative feedback. But in cases where the SSTs are not near the deep convective threshold, increase in temperature warms up the area and it reduces the cloud, the lower level clouds, increasing the boundary layer thickness, and that can be a positive feedback. And if you look at different models show different things. And what I'm showing here is just the observations and the model simulations, ECSM V2 on the left, and ECSM MMF on the right. And if you look at this, so you can look at, so this is the anomaly of SSTs on the x-axis, and the anomalies of zonal shortwave heat flux, both over the Nino 3 region. And what you see is it's a negative feedback, meaning as you increase the SSTs, you increase the shortwave, you decrease the shortwave fluxes. When the SSTs are above the deep convective threshold, when they're lower, the observations say that there's no feedback. But in E3SM V2, we have this positive feedback here, and absolutely no response to SSTs of shortwave fluxes. But once we add the MMF, where you have deep convection explicitly being simulated, then the negative feedback in the positive SST regime, positive SST anomaly regime, is much closer to observations. And then this negative feedback turns to positive feedback in that case, which is slightly different from the observations. But overall, it seems to be an improvement over the E3SM V2, meaning that it can replicate this negative feedback in the model. So an implication of that is that if you do a regression of shortwave heat fluxes against the Nino 3 over all the tropical Pacific, you can see that there's a big reduction in the bias in the model. So this is E3SM V2, and regression of shortwave heat flux against Nino 3.3, Nino 3 index. You can see that there's this big dipole, which is much weaker in the E3SM MMF. And it also means that it might impact the variability of shortwave heat fluxes in the model. So on the top here you see is the standard deviation, just the interannual standard deviation of shortwave heat fluxes in E3SM V2 and E3SM MMF there. And these are the observations, and these both are the same thing. What you see is that there's a bigger variability that you see in the model, but you don't see that in E3SM V2, which is much stronger than the observations, and this bias is much reduced in E3SM MMF, which means that there's strong coupling between SST and shortwave heat flux, which implies that it's tied to this ocean in those regions, which means that if the variability of the ocean is low, then the variability in the shortwave fluxes and deep convection is also very low. And the second feedback is the weirdness feedback, which is if you increase the SSTs in the Eastern Pacific, which means you reduce the wind stress over the tropical Pacific, which means that you bring in more, which increases the flux of water from the Western Pacific to the Eastern Pacific, and which warms up the SST further. And so this is again observations versus model. And what you see in the model, in the observations, it's a positive feedback, which means that increase in SST in the Nino 3 region means that there's a decrease in wind stress increase in wind stress in the Nino 4 region, which are different boxes of the Pacific. And this is very similar between the E3SM V2 and E3SM MMF. This implies that although the MMF can improve your shortwave SST feedbacks, it does not help with the wind stress SST feedback. And so the biases that are associated with that would still exist in the model. And the other thing we noticed was, so this is just one run of ETSM MMF, that's all we have. But for this run, ETSM V2, we have several ensemble members, and I'll show a few of them here, which are 4 here, and what we see here is this strong bias in the zonal stress wind field, which is not seen in the observations. So all the dots here are observational data, and what you see here is some of the ensemble members are producing this strong variability in zonal wind stress, which is not seen in the observations. So that's one thing I found. I just wanted to mention that. I've not looked into why that might be. And what this with this weakness, this poor simulation of the weirdness feedback means is that you'll have this errors in the tau x or in the zonal wind stress variability. So what you see here is the ETSM V2. This is observation, and this is a regression of wind stress against the Nino 3 index. And what you see here is there's a low bias in the ETSM V2, and it does not improve much in the MMF model, meaning that the bias associated with the weirdness feedback is not improving in the model. And then if you look at the mean state, there is this SST Colton bias, which means that the SSTs are much weaker over the equatorial Pacific in the ETSM V2, and does not change much in ETSM MMF. And then we have this increase in the zonal wind stress, which is much stronger in ETSM V2, and it's also strong in the ETSM MMF model. And another implication of this is the variability of zonal wind stress in the model. So again, this is ETSM V2. That's the observation, same in both sides. That's the difference between ETSM V2 and observations, and that's the difference between ETSM MMF and observations. And we see that there's a strong variability in a strong reduction in variability in zonal wind stress for both the models. And this is not the MMF is not helping with the zonal wind stress simulation at all. The other thing we talked about was the El Nino, the diversity in ENSO, and for that I use an index called the ENSO longitudinal index. It's a newer index that was devised by Williams and Patricola in 2018. And what it looks at is the location of the SST anomalies in the tropical Pacific. And what you see here is the climatology of SSTs for 2 seasons here over the ocean, over the tropical Pacific. And then you have this index, which is just the average of longitudes that have the tropical Pacific, which is greater than the mean SST of the global tropics. So the mean SST of global tropics can be considered as a threshold for deep convection in some ways. And once you cross that, that means you're having a convective regime. And so what this index tells you is that, and you take the averages of locations where you have that, where you have deep convection. So if the value of the ELI index is more, that means the ENSO event is happening more towards the Western Pacific or the Eastern Pacific. So this is an example of that. As you increase the value of ELI or the ENSO longitudinal index, what it tells you is that the SST anomalies are moving towards the west, and you have these warming in the Eastern Pacific. And what they showed in their another paper was that if you use this index, then the signal that you get from a strong El Nino with the ELI index is much stronger than what you would get with a stronger, if you just use the Nino 3.4 index, for example. And the same thing holds for this La Nina case. You get these stronger anomalies here, but not so much here if you just use the Nino 3.4. So that helps to capture the effect of ENSO diversity on the teleconnections, for example. And so this is just a scatter plot showing that effect. So this is the Nino 3.4 index, and this is the ELI index. The green line is for the green squares are for the observations. What you see here are 2 dots here. This is the 82 and the 96 events, which are the strongest canonical El Nino events, and they had anomalies right here in this region. So these were very strong events. But 2015 event was somewhere here, which was just a regular strong 3.4, Nino 3.4 event, but it didn't have any warming in that region. And so that's why we didn't have, so they claim that's why we didn't have a strong response in this region during 2015, 2016. As we see here for the 96 event, for example. And this also shows some results from the E3SM V1 run. So the circle point to the V1 low res, and the triangles point to the V1 high res. And we see some improvement with the model, likely because of the improvement in some convection in the model, because it's resolving more processes. And that's that plot, that's the PDF of the ELI index itself. So in this case, it's green. And the green is the observations, the blue is the low res, and the red is the high res. You see that shift towards the right with high res. But if you look at other models, then we don't see that a clear resolution dependence, and this is a big spaghetti plot of that. So the black line is the observations, and each of the dashed line is the low res model, and each of the solid line is the high res model, the equivalent high res model. And there's no clear signal of improvement with resolution. So it remains a complex issue. And then with ELI, if with E3SM MMF, we still see this this ELI being towards the west, which is similar to the E3SM other E3SM models, meaning that it's not helping with the diversity of the model, ENSO-diversity of the model. Now, the impact of this reduced SST has on the impact of ELI can also be seen in the variability of SSTs, for example. That's E3SM-V2, that's the observations. And there's a standard deviation, interannual standard deviation of sea surface temperatures. And what you see here is that in E3SM-V2, for example, there's this weak variability in the Eastern Pacific, meaning that it cannot simulate those canonical events better, nicely. And in this case, in E3SM MMF, we still see the same kind of biases, meaning that this diversity is not simulated properly, and it may be likely due to the weirdness feedback, which is weaker in both the models, meaning that it's not allowing the zonal wind stress to pull up to upwell water properly there, causing stronger El Nino events in the Eastern Pacific. Now let's look at teleconnections and look at extremes for that matter. And so this is showing the GV distribution for the parameter mu, which is the location of the PDF of extremes. That's observations, that's low res, and that's high res model on that side. And we see that there's an increase in extremes in the high res model just because you're resolving more fine scale processes, orographic lifting and things like that. And you see some improvements with the Great Plain region. And the difference between E3SM-V1 and high res and low res is not just resolution, there's also some changes in tuning. So if you change the tunings back to what it was, or change the tunings in low res to that of high res model, and run it again, you still see that it doesn't really help that much. You need some resolution to improve the simulation of extremes in the model. And so as I said in the beginning that you can compute return periods, just to show that you can invert that probability distribution to get the return period of extremes, for example. And it's just showing that it looks very similar to what we saw here. So we just look at change in mu, for example, we'll expect this to have an immediate impact on the return periods too. So an increase in mu also means an increase in the return value for any time period. Okay, so let's look at just the mean teleconnections in the models. So on top you see CPC teleconnections against ENSO or Nino 3.4 index, and what you see here is that the model is that the observations show strong signals over the southeast US and the southwest US some, but the dashed line here show the significance. So the only regions that show significance are these two regions. Otherwise, everything else from observations is mostly noise in the system. And if you look at low resolution simulations, you see similar results, but with a weaker amplitude in the southeast US, a good amplitude in the southwest US. But in the high resolution simulation, we have much stronger impact of ENSO on the southeast US, closer to observations, and not so much in the southwest US. And then we can look at, so that was the mean response. We can look at the extreme response, which is using this GEV framework, generalized linear modeling. And we add this alpha parameter to the location parameter, the mean parameter of the GEVs, and you can compute that. And this is what's shown here. So what you see here is that, again, in the Southeast US, we have a strong teleconnection compared to with the ENSO, both in Southeast US and a few grid points in the Southwest US. And in L'Aurore's model, we have some impact here, but it's much weaker. Nothing on the Southeast or Southwest US. And with the high res, there's a much stronger response compared to observations, but not so much in the Southwest US. And then we can look at the diversity impact too. So instead of the Nino 3.4 index, if you use the ELI index, which Patrick and her colleague showed, that you get a stronger signal in the extremes over the Southwest US and also some over the Southwest US in the mean sense. And if you look at the low resolution model here, we get some signal here, but it's weaker than the observations, but some signal in the mean sense. And the extremes, again, the high resolution model shows a stronger response here and a stronger response in the Southwest US as well, both in the mean sense and the extreme sense. So that means that the high-res model is better able to capture the ENSO diversity, the impacts of diverse ENSOs on the teleconnection pattern. Now we can look at this in a bunch of models. So this is showing the same thing for different models. So ETSM1 is here, ETSM2 is there, and these are the other high-res MIP models. What you can see is, in general, over box A, which is the Southeast US, we see an increase with resolution. In 4 of the 6 models, I think, that one, and this one, and maybe a little bit this one. But overall, it doesn't show a strong sensitivity resolution. But the Southwest US, you see improvements in most of the models. You see that one, and maybe that one. Okay, so 6 out of the 7, I think, showed improvement in Southwest US, and 4 out of the 7 showed improvement in the Southeast US. And yeah, so that's the table there. There's a reduction in these models in the bias in the Southwest US by quite a significant margin, but then the MPI model showed a big increase. And then for the Southeast US, we have this metric again, but while there's a decrease in the bias in 4 cases, there's an increase in 3 other cases. Yes.
Yeah, and those locations seem to be the places with the possibly biggest impacts from the precipitation.
Yes.
But what about high impact for megalopolitan Northeast United States? It looks like in some of the simulations, you go all the way to Cape Cod with a significant increase when it's high resolution and it disappears in the low resolution. Is that realized in the observations?
So it's not. So that's the whole issue with this, is that if you look at here, this is data point, but it's not significant. So you cannot say something from the observations.
Okay, I thought I saw hatching there.
Yeah, the significance is shown by these hatch lines. So even here, it's not everywhere, it's just a few points.
Thanks.
So it's very hard to get this. And we were really tight here to find the significance. We used the student's t-test, but we also used a method called the FDR, which is called the false discovery rate. Because you're doing tests on like 1,000 points, 5% significance test would give you 5% wrong conclusions by nature of the design of the test. So we made sure that that's corrected for.
Okay.
And so it's very stringent there, so to figure out if it's really there or not.
Thanks.
So what I was saying is that in some of these, the other models, there's a strong increase in the bias, right? So it's not really a clean answer if resolution helps with teleconnections over the US. And then we also looked at the MMF, of course, and then this is observations, the same plot, and this is showing MMF results, and you see that there is some response, but it's much weaker than what's observed, likely because the resolution here of the grid of the base model is 100 kilometers, which is similar to the low resolution models. And so even to get a proper teleconnection, you need a high resolution base model, likely to get a good answer, even though you're resolving convection better. So now we looked at what was the driver of these extreme responses or the mean responses, and what I'm showing here is some basic diagnostics, looking at the linear regression, of Z500 and moisture transport on the ELI index, for example. You will see here is this extension of these westward extension of the negative Z500 response into the southeast US in all the three models, but it's the observation is much stronger than what you see here in the low-res model, but it's and the high-res model. And what you see here is that this has an impact on the moisture transport, which brings in moisture into the California region and also into the Gulf of from the Gulf of Mexico to southeast US, which is much better simulated in the high-res model. And this is because the moisture is able to have a cyclonic response in this region, which was not there in the low-res model. And we can look at that for all different high-res models that we have. So we didn't have data for these two models for the moisture transport, but for the Z500, which is the teleconnection pattern, we had responses, and we see that in the southwest US, there's an increase in moisture transport in most of the models that show an improvement in the extreme response, for example. But over the southeast US, what we see here is that most of the models don't converge the moisture into the land area. They just have it pass through over the panhandle of Florida and across into the Atlantic Ocean. And we don't see this moisture convergence into the Gulf of Mexico, into the southeast US to have a strong precipitation response in those regions. So they also looked at some basic metrics like storm track activity, which is defined as the standard deviation of Z500 in the 2 to 6 day period. And so it's just capturing the variability on a high frequency, meaning that it's showing places where it might be that might have high strong track activity, and then a regression of that on the ELI index. What you see here is that in observations, when you have an ENSO event, there's an increase in storm track activity over the Gulf of Mexico and Southeast US. And if you look at the low-res model, it's there, but it's weaker. In the high-res model, it's also there, but it's also weaker. And what the other thing you can look at is vertical velocity and feedback processes, meaning that if you have precipitation, it would heat up the upper troposphere or the free troposphere, and which would then suck in moisture from the Gulf of Mexico, which would then cause more precipitation, which would increase the vertical uplift further. So we see these strong uplifts in observations or reanalysis, and not so much in the low-res model, but a very strong response in the high-res model, close to the coast. And then we can look at, again, for different models. So we had 5 models that had the data for this, and we see that the response is not really tied to storm track activity in some models. For example, in high-res model, in the high-res E3SM V1, the response is a little bit better. In V2, it's better, but it doesn't result in simulation of extremes. And then we have this in this model, which has it's very sensitive to that in that region. So it's a mix of moisture transport, the storm track activity, and vertical uplift, and the feedbacks between precipitation and uplift, which as a mechanism. And we see that in these models with high res, there's an increase in vertical uplift in some cases, but these feedbacks are not very clear as they were in the high res V1 model. And so it remains a complex problem. So there's biases in ENSO, but there's also biases in the drivers that drive the precipitation extremes over the US. And if you look at it carefully, you can make some sense that it's a combination of storm track activity, moisture transport, and the vertical uplift. And then we also looked at the MMF, and again, so MMF is very close to observations, and so we have this strong simulation of the storm track activity, but that does not result in strong precipitation there, likely because of the lower resolution of the model. And then you can look at uplift again, same kind of analysis, and you see that there's no, even though the storm track activity is very strong, the uplift from the in the region is not there, but it happens over the southwest US. And again, you can look at moisture transport. So there's moisture convergence in the observations in the Gulf from the southeast US from the Gulf of Mexico, but here the moisture is just passing through the Gulf, the Panhandle, and over California there's some moisture transfer into the region which is stronger than observations, but does not result in precipitation because of the lower orographic lifting in the ETSM because of the lower resolution. And then we can look at it deeper, a little bit deeper, and look at the moisture transport during extremes. So this is looking at precipitation over this box and regressing that on the moisture transport or a composite of moisture transport only during extreme events in this box. And what you see here is when you have an extreme event here in precipitation, there's a strong moisture transport into the region in the observations. There's also strong moisture transport in the low-res model as well as the high-res model. But during ENSO, so this is saying that anytime there's an extreme event here, there's a strong moisture influx into the region. But if it's an ENSO event that is causing an extreme event in this grid box, what you see here is that there's moisture transfer into the model, into the region in the observations, but not so much in the low-res model. But we see that in the high-resolution model where it brings in moisture transport from the Gulf of Mexico, but not as strongly as the observations. And then you can look at the vertical fluxes in the model, and you see that there's some increase in vertical fluxes. Let's ignore that. I don't remember which model that is from. Oh yeah, this is just a repeat of the low-res and the high-res model, showing that in the high-resolution ETSM V1, there is an increase in the vertical flux uplift in the high-resolution model as compared to the low-resolution model, and saying that. And then if you look at the extreme, if you look at the vertical mass fluxes during extremes and during extremes and during ENSO extremes during ENSO events, you see that in the high resolution model there's this big increase in vertical uplift during extreme events here, which is also seen here, but the moisture transport is not there in that, so that doesn't cause that increase in precipitation that you see in high res model. And then we also did some, so up here the story being that there are mechanisms that are active in the model, and some models simulated, but there are processes that are deficient, and both in the simulation of ENSO as well as in teleconnections. And then the other problem, as we see, was that there's no statistical significance of the response from observations, and even from models there's not much because of the lack of data. So what we did here was we did some targeted simulations with this E3SM V2 framework, where we did short ensembles with prescribed SSTs. So the SSTs don't, it's not a coupled model, just SSTs are prescribed to the tropical Pacific, to the 97, 98 El Nino condition as one set of simulations, and 2015, 2016 as to replicate that event. This is the canonical event with the Central Pacific El Nino event, and then a La Nina case, a strong La Nina case in 2010, 2011. And then we look at this, we do these short simulations, 24 members, so we have strong samples, a big sample size, and then we look at the difference of that. And what you see here is a difference between two suites of ensembles, one with the strong El Nino case minus the strong La Nina case. And what you see here is that yes, there's a significant response here. In the Northeast, there is a response here which is also significant if you have a big sample size. And with Southwest US, we don't see that much. And if you look at the difference between two different ENSO types, then you see that yes, if you have a Central Pacific ENSO, you have a strong, or if you have a East Pacific El Nino, then you have a strong response here, but not so much there. And that's what we saw during 2015, 2016. And so the model is able to replicate it if you reduce the biases in the model by prescribing SSTs, for example. So this is just a list of the things that I talked about. Model biases and so diversity are linked to poor representation of the erroneous feedback mostly. The MMF improves shortwave heat fluxes. 6 of the 7 high resolution models are better in the Southwest US, 4 in the Southeast US, and then they have stronger extremes in most cases. And there's this bias I didn't talk about in Pacific Northwest, but there are strong biases in different processes in the model, and you can partition what's causing what. And what we found was that improved Southeast US precipitation is likely because of the moisture transport, and over the southwest US, it's storm track activity plus the moisture transport. And there might be a feedback in the southeast US that may be active in the high resolution model, but it's much weaker in the low resolution model. And then we find that, of course, biases in ENSO diversity persist in high resolution models, and it's not really clear if resolution only can help solve that. And there are other future things where you can do this. So given I have 5 more minutes, and this is the same thing talking about MMF. Let me go quickly towards this other study I'm going to talk about in 5 minutes. So now we know that the models are not doing very well in terms of simulating ENSO teleconnections because of different reasons. And this is a plot just showing that again for seasonal forecasting. And what you see here is the correlation between ENSO or Nino 3.4 and precipitation of California. You see it's very weak, there's very little signal over in some places. This was another study that showed that the R squared from ENSO and PDO together is only about 0.2. And then the correlation in monthly scales in a recent study showed that it's almost nothing. And then this is that the thing we talked about in 2015, 2016. The prediction was an increase in a strong precipitation over California, but actually what we saw here was a strong reduction in precipitation here and an increase there. So dipole, this dipole, and so this is positive and negative here, and this is negative and positive. Or the other way. So we had a completely opposite opposite response to what was expected or forecasted by seasonal forecasting model. And so recent studies have shown there's a lot of skill that can be extracted from machine learning approaches. This is an old paper now in machine learning terms, which is 2019. And what they showed was if you use a convolutional neural network to predict ENSO and different types of ENSO, they can do that much better than all the seasonal forecasting model, going all the way to 18 months with a correlation skill of 15. But that only stands for the ENSO itself, the strength of the ENSO, but not on teleconnections. So what we wanted to do was look at it in a slightly different way and look at nonlinear PCA or autoencoders in modern language. This has been done before, where you can, instead of doing a PC or EOF analysis, you can do a nonlinear EOF analysis, and you get different patterns of La Nina and El Nino. And so what we wanted to do was look at this in the multi-modal sense. We take both data over the tropical Pacific as well as over California to see if we can improve predictions there. And so we designed a network which we call the multi-input, multi-output autoencoder. We take data from the tropical Pacific and from Southern California region over this box, put it in one-dimensional arrays, and then we have a feed-forward neural network to predict the same thing through this network. And here what we are doing is we are forcing this network to learn the cross variability between California and tropical Pacific by making sure that they go through one node, and then we have to bring them back again so that they can reproduce this. So what this node is learning is the shared nonlinear latent space between these two regions. And now this has, this node, if you pass data from each month, you can bring out this value, which is a scalar for each time you pass some data through it. And once you have that, this has information from SSTs from the tropical Pacific, which means it has some memory and some predictability to it. But this is also associated with precipitation here. So if this is predictable through that, maybe we can get some signal of California precipitation from that shared nonlinear space. And so for this, we didn't take much data yet, but that's our plan. In this case, we took E3SME1 simulation. We had 100 and some years of data from that, and we had observational data, and we trained the model, trained the network on both the simulation as well as the modeling data. And this is just a list of those, what we used. This is training loss. And what you see is once you train this network and reconstruct SSTs through that network, so you pass data through this network, and then you come back again to reproduce that data. What you reproduce is a pattern like this, which is similar to ENSO in this case, a little bit, but you see that the variability, as it explains, is only at about 30% at the maximum. And here, we're explaining about 80 or 90% of the variability over California. So if we can predict this somewhat, we have a very strong signal from there. So this is just showing a time series, which is, so what you see here is the precipitation black line, then the Nino ELI index, for example, in the green line, and the MIMO A index, which is the autoencoder index, in the blue line, and it's highly correlated with precipitation. And if you look at correlation between Nino 3.4 and precipitation over California, it's only 0.26 or such. And so we can skip over that. And you can look at the observed top 10 events and reconstruct that pattern from the SSTs. And what you see here is that for the top 10 events, you get a pattern like this, which causes this predictability over here. And then for negative cases, we get a pattern which is opposite, but not really, because this pattern is slightly different. It's a nonlinear index, so you won't expect the exact replica. And then this is again looking at these reconstructions for different years when you had very strong El Nino, and you see that when we didn't have a response with the California region, the pattern here is almost nothing. But for these two cases, we have a stronger pattern here, and a slightly weaker pattern 82. And then we had this index that I showed you here, and then you can use this blue index, for example, and then try to predict it using autoregressive model or a LSTM model, in this case, to add some nonlinear components to it, which is here. Let me skip through that. And what we see here is the correlation skill of the index itself, which is in the blue. So this is time forward. This is this 1, 0. This is not 1, it's 0, 1, 2, 3, and in lead times. And we see that Nino 3.4 has some predictability to it. ELI has some predictability to it, and this blue line is the index from the network. Autoencoder network, it also has some predictability, which is more than just the precipitation. And you can use the network again once you predict the forward time of the index, and then you can put it through the network again to extract the precipitation. And what you see here is this increase in index, increase in predictability to 0.6 as opposed to 0.2 or 0.15 from the ELI and the Nino index moving forward in time. And and so that's the summary quickly, that with an architecture like that, we are able to extract predictability over the California region. And we have expanded this work to include more variables from the atmosphere. And we have looked at predictability over the southeast US, which is where you also see some signals, and also the Amazon. And then we have also looking at the impact of Arctic sea ice on predictability over California in those regions. And so some future work ideas, but mostly acknowledgements to the computing facilities we have in the Department of Energy complex, HSM project team. Take questions.
All right, questions, and let's start with questions from students. Rudra.
Hey Salil, great talk. I'm just wondering that from the figures you showed about high-res and low-res, would the regions which are on the far west Pacific and processes that go over there, mostly convection or MJO, would those processes and how they are resolved would also be affecting your teleconnection patterns, and whether there are improvements in those biases?
Yes, and I have not looked at that yet, but on the seasonal timescales, they may be important, and that's the plan, to expand the work to include MJO indices in that GEV framework, for example, and to see if the MJO dependence is real in the teleconnections at least. But in this autoencoder work that we saw, there is inclusion of SSTs. So if the SSTs are driving MJO, then that's inherently included in that network.
Thank you, Salil. Really interesting. It seems to me the modeling is getting to the point now where we can look beyond the details of just the big teleconnection patterns and actually ask ourselves, what's the array of cyclones in the mid-latitudes that come past the Gulf of Mexico that lead to the variability in 500 millibar vertical motion during an El Nino season and in a non-El Nino season? Is that something you can imagine putting into this broad framework?
Yes, I can, but here I took the easy approach where I just looked at the standard deviation of Z500 on a bandpass filter to 6 days. So That's a proxy for cyclones coming through,
Yeah.
but not really. So I could like easily run a tool that counts these storms that are passing through and seeing that, but ultimately it'll give you something similar because it's the large scales that matter, and they are being driven by the ENSO biases inherently in the model.
Yeah, I would
So
say,
it's-
I'm sorry, go ahead.
Yeah, and yeah, that's,
I was going to say, as a follow-up to your last comment, yeah, the large scale does determine whether cyclogenesis will occur in a broad
Yeah.
region. That's true.
yes,
But the nature of the resulting cyclone depends on something that's a little bit smaller than the large scale.
Yes,
And I
definitely.
wonder if that is a factor in producing, some of the differences that you see from one type of season to another in terms of the vertical motion at 500 millivolts.
yes, definitely. So here we only looked at the winter season, so not the summer
Yeah.
season. So that takes away cyclones like hurricanes, for example.
Yeah.
But when you're talking about extratropical cyclones, and I agree, yeah, we need a better metric to
Yeah.
properly quantify it.
Yeah, it's really interesting.
Just kind of following with that, I wonder if that is connected to, one thing that I noticed is that whenever you went to higher resolution, there was a tendency to over-suppress precipitation in the Pacific Northwest. right
Yes,
along that
that's a
coast.
bias in the system, yes.
Yeah, I wonder if, because do you have a sense, I guess, as to why that might be?
Yeah, it's again, I think the large scale, I can show you something.
I didn't know if like because
Yes.
it shows up when you increase the resolution.
Yeah, so we increase the
right?
resolution, and this pattern that's here drives moisture into that region. It creates that pattern, and this is what you see in a lot of the models. Yeah, see that one, right?
Yeah,
It seems, yeah, it
I
seems like
wanted to see that.
it's again a mix of storm track activity and then moisture transport into the region. Yeah, it's there in all of the models.
And, I'll just follow on that. 'Cause some of the cyclones in an environment that's got ridginess in that location will
Yes.
not occlude.
Yes.
And they won't wrap up, and so they won't be as stationary, and they won't be as substantial a precipitation threat. And I wonder if that's not reflected in some of these things. That's kind of what I'm
Yeah,
getting at.
yes, probably, yes. But these days there are lots of tools that can look into it, like track the cyclones. going
Yeah,
through.
that's right, that's
So, yeah.
right. I mean, and I think this is the first time ever that seems to have been the case, that your community looking at the large scale environment and how it evolves in models can really start to talk to the community that looks
Yeah.
at the sort of smaller scales.
Yes, yes.
And that's really exciting.
Yes, but the thing is, the ENSO is not just teleconnections, it's also ENSO itself. So unless we resolve ENSO properly, we don't know what's causing the biases in teleconnections.
Yeah.
Right? So,
Yeah, and for my money, I'd want to know what the jet looks like in every one of these
Yeah.
cases, because that's what links the two, in my opinion.
Yes.
Yeah, it's really cool. It's really neat.
You get a sense for how that breaks down. I mean, there are the biases in ENSO that still exist in this model, but
Yes.
then you've got all the, I guess, like say vertical structure of heating versus
Yeah.
the mid-latitude jets and the propagation characteristics.
yeah, it could be a mix of things. I really don't know, like how do you extract what's causing what? And the best is you do an AMIP-like experiment and see there, but then you're decoupling the ocean to the atmosphere. How realistic is that?
But it is interesting to see that locally, when you look at the extreme events, it is capturing the moisture flux correctly, say in the southeast U.S.
Yes.
And so it's not an inability to capture the moisture fluxes.
Yes, it's the inability of the ENSO to
connection.
drive the moisture
Right,
transport
right.
that causes that.
Yeah. So it's
Yeah.
we're left with once again ENSO having those biases and trying to figure out where those are coming from, which is a tricky problem.
But
This. Oh.
I
Let's
just
go
got-
with you, Liz.
Yeah, yeah, yeah.
I think I was
Yeah.
going to ask an ocean question. So at the beginning, I think you said that when you improve the resolution in oceans, it tends to improve ENSO.
Yes.
Right.
It seems like it.
Right.
But that's just one model,
Okay.
one ocean model.
So I think I saw the high-res mix simulations in there.
Yes.
I'm curious, did you notice from those papers or from your experience with this, have you noticed that the improvement in, like, at a certain resolution, the ocean starts to improve things? So like, I'm thinking that there's a big difference between an ocean model that resolves eddies versus permits
Yes,
eddies.
so-
And maybe each model has a different threshold kind of
Yeah, so this is mostly eddy resolving models in the framework that I've seen that have them. So some of them have resolution of 10 kilometers in the ocean.
But that's
show
not
that
what these are.
Yeah.
Or these are.
Although these are, some of them are, I can show you that too, I think. So they're not 10 kilometers everywhere, but they go to that resolution. So 8 to 16, for example, in E3SM, only for the mid latitudes, I think.
Okay.
Yeah, but the high res MIPS are not.
I was just going to say, is there, just in response to what we were having as our conversation, is there room in this kind of analysis, and would it be insightful to interrogate the synoptic and larger scale structures, like jets, like other things, that actually populate the biases?
Yes, definitely.
Okay.
Yes, jet streams are easy to look at.
Okay.
Things like that, yeah. But I thought when I looked at these storm track activities and things like that, it's covering most of those things, and you would see something similar. I didn't go deeper in that.
Yeah, except you might have different thermal advections
Yeah,
along
yeah.
the jet, and some synoptic
Yes.
details can really matter in some of
Yes,
those cases.
yes.
I don't know if they systematically matter, that's why I guess I'm asking.
Yes, yes, I understand.
All right, thanks again. Last thing, if anybody wants to get in touch with Salil, I'm not around tomorrow, but you can get in touch with me and I can send on information. We do have I think Oak Ridge and UW has some sort of like an MOU thing, and there's lots of visiting opportunities as well. So if you're ever interested in that sort of thing, we can get people.
Yeah, and not about this work, there's other people who do a lot of interesting work, so anything if you're interested in, you can contact me or them.